Hello, this is Dr. Kozhanov again, and this is online lecture 3. Lecture 3 is dedicated to domains. So we already encountered domains in previous lectures. And the first time we encountered that, if you remember, we discussed that ferromagnet might have a magnetization aligned in different directions, so it can be pointed in different directions, but these magnetic moments do not necessarily need to be atomic magnets, because in ferromagnet there is a exchange interaction between neighboring magnets. So all neighboring magnets are aligned in one direction. Neighboring, by neighboring I mean the atomic, let's say iron atom, iron atom, iron atom. But if you have a big piece of material, big macroscopic piece of material, then it is not typical that all atoms in the material are aligned in the same direction. So while they're aligned ferromagnetically within a certain area, the different areas of the magnet might be aligned differently. So one area might be magnetized in one direction, another one is in a different direction, third one in a third direction, etc. So what that results in is if we have a totally random magnetization of areas of ferromagnet, then overall magnetization can be zero. It is possible that you have a magnetized material but not magnetized macroscopically. So now excuse me, let's talk about domains. So if we look into, I'm using this tool, if we look into the hysteresis curve, then hysteresis is magnetization axis, this is magnetic field. Let's take a ferromagnet with a remaining magnetization. So it's magnetized at zero magnetic field, this is 0. And as we apply magnetic field, it magnetizes completely. When it goes back along the same curve, and then it can reverse magnetization. And then on the way back, it can magnetize in this. So this value here is our saturation magnetization. This basically, as you know, represents the case when all magnetic moments point in the same direction. It means that if you have material, then if you look at it microscopically, you will see that all magnetic moments are aligned along the applied field. And in this case, the field, let's say we will apply field in this direction, H. Okay. So now, by looking at this, you can see that the magnetization is at zero magnetic field is smaller than saturation magnetization. So we can write that M is smaller than MS for some fields. And what it means is that not all magnetic moments are aligned. But we know from, if it's ferromagnet, let's say if we'll take iron, for example, we know that in these materials and neighboring spins are neighboring magnetic moments are aligned because it's defined by exchange interaction. So what it means that this is the first thing that leads us to think that there is different areas with different magnetization. Now there is a certain there is a history of that. So first of all, we already discussed in previous lectures, let me use different color, there is this Mace domain theory. So Mace introduced, as you remember, the molecular field HM that is proportional to magnetization. This can be gamma, or sometimes you'll see alpha. But this is molecular field And molecular field is responsible for spontaneous magnetization, so the interaction between different atoms is explained that way. But also it explains why we might have a material that is magnetized but not magnetized completely, so that there might be domains. And if we'll talk about history, of this, then there is a certain several certain experimental observations. So let me put it here. And so first historic observation that indicated existence of domains was so-called Barkhausen effect. Now, if we look at the hysteresis curve right here, you'll see that the magnetization grows. If you'll start magnetizing material from completely demagnetized state, then it would go something like that. It will initially magnetize there. Now, how does it magnetize? What is the magnetization process? So magnetization process, what we'll have to do is we'll have to do closely into this line what's happening in here. So at certain magnetic field. And if you look in here, I have an image to show you instead of drawing. So this is how it will look like. Now I took this image from a non-credible information source, Wikipedia, but it's a good image to see. So if you zoom in to the hysteresis curve, and you see that's a J magnetic moment, or B, the magnetic field flux, but if you remember, B is defined by mu naught H plus M, and at a given magnetic field, it is magnetization that mainly contributes to B. So if you will look here, you will see that this curve, it doesn't go up smoothly, but rather there are some certain steps. So it goes up in steps, so it stays constant and jumps up, constant, jumps up, etc. So it is not typical for analog analog system like materials are analog systems. Things are moving continuously. So it's not typical that these systems exhibit these steps. So as if it looks like a quantized system, but with many steps. So that was the first thought, that when you have a material that magnetizes, then the magnetization of the material might go, let's say you have one area of material magnetized this way, other material magnetized that way. And here are two domains. We already know about domains, but that was the initial thought. So if you apply magnetic field this way, then what happens is that this magnetic field is favorable for this magnetization. It's anti-aligned, so energy is pretty high for this magnet, and we'll talk about energies a little bit down the road. And what happens is that this boundary here, which is called the main wall, starts to move that way. And if it would be moving continuously, then we would have a continuous, instead of having this, we would have a continuous growth like that. But what happens is that materials are full of impurities. And when you have impurities in the materials, the domain wall, the magnets interact with impurities, and it pins their magnetization. So what is happening is you basically have domain wall pinning on impurities and then unpinning from impurities. So again, I will show you another. So it doesn't show as GIF, but I can show it here. Oh, let me do this. So you can see this is the domain wall. It moves through the impurity and pins. So it goes through the impurity and unpins suddenly. So these unpinning processes are responsible for the jumps, and you can see the magnetic field increases. So what it means is that at certain magnetic field, you have the domain that takes a certain position, and you have to apply a higher magnetic field for the domain wall to get moving forward. And while the domain wall is bent, you have magnetization that's not changing. So that's one of the experiments that was indicating the existence of ferromagnetic domains. The other, a bit more straightforward experiment was published by Bitter. That's 2. Second experiment. So what he did is, in order to study the magnetization layout, you know that if you want to visualize magnetic field, what do? You use iron fillings. That's what you did in the introductory physics experiments. So you take iron fillings, you put them, and then they show you the direction. They align themselves with the magnetic field. Now, iron fillings align because they have sort of elongated shape and they align themselves. But if you have a small powder, so if you have magnetic powder with a very, very tiny particles, then these particles can get magnetized, and they would concentrate in areas with a certain magnetic field direction. So one of the textbooks that I advised for this class was by David G. And if you look at chapter, I think 6 in that textbook, that is the chapter dedicated to domains, it has some nice images which I will show you. Basically what was done by Bitter, and that was a Bitter experiment, is that he took a piece of ferromagnet and he used a magnetic powder in liquid and poured it over. So he poured that magnetic over the magnetic material. Now liquid allows, there is no friction, there is very small friction. So liquid allows small magnetic particles, powder particles, to move freely over the surface. And the forces on these magnetic particles are defined by the magnetization. So if you have magnetization here pointing up, and in this area it points down, then what happens is that magnetic field goes up and down, like this in this area. And for particles, this force can, the particles are magnetic, so there are forces, magnetic forces exerted on them, and particles would tend to accumulate in between these two areas. And what would happen is that basically the particles would accumulate in the areas that are boundaries between different domains. So to illustrate that, there is another image that I would like to share. This is the image. So this basically illustrates the mechanism. So you see, if you have a magnetic film, and in this case, this is illustration, there was a multiple publications that use this technique, and actually it's called a Bitter technique. So in this case, this is cobalt, and cobalt is typically used for magnetic recording. So magnetic recording, this is audio tapes, this is magnetic recording that's used in data storage, that's magnetic recording that's actually nowadays is used in computer hard disk drives. So if you'll take cobalt film, and this is a cross section of the cobalt film, and then areas of this material can be magnetized vertically either up or down, because it has anisotropy axis. So this is easy axis, as we learned from one of the previous lectures, vertical. So magnetization wants to be aligned either up or down, and areas of different magnetization alignment alternate. And you can see if you put magnetic powder, and it's all in liquid, so it's all in liquid, then these magnetic particles would tend to accumulate in the areas between the domains. Now, if you look at the top of this film, and if you look at the top of this film, then this is something that I'm going to show. This is something that you would see. So this is figure 6.4 from the textbook that I advise for the course by David Gillette. But so this is actual microscope image. You can see this is magnetic domains, and it was published by Williams, and you can see that it is called bitter method. Let me use different color to highlight things. Yeah, so bitter method. Bitter was the first to do this experiment, and the method is named after him. So you can see that this is an image where white indicates the powder. White indicates where the magnetic powder particles locate themselves. And these white lines on the dark background is basically the shape of magnetic domains. So you can see it under a regular microscope. And then this information of the domain shape can be used to extract the magnetization alignment. So they take this pattern indicated with a line. I think this portion is a portion somewhere here, taken from somewhere here. And magnification is 120. That's not too much. It's a regular microscope. So if you take microscope with a, I don't know, eyepiece 10 eyepiece magnification, then you'll have to have only 12 magnification of this. So this the magnification of microscope gets you can get it from eyepiece magnification and the microscope objective lens. So it's not too much, 120. So you can see them visually at macroscopic scale using this method. Okay, so that was a bitter experiment. And actually, if you look at scientific papers, and I will pull up one of them for you now, it is a common technique. The reason why I'm pulling up the paper is to show you, this is the paper published in Journal of Magnetism and Magnetic Materials. You can see that it is bitter colloid observations. So bitter uses this powder. The one thing that I would like you to note is the year. It's 1993. So 1993 is 20 years ago, but it's a well-known method. Nowadays, there are other methods that are used, but if you scroll down, you will see I took this image for you from this paper. And this is what they observe. So they actually publish these microscope images with very strange patterns and make some conclusions, but more than that, you see, they illustrate the bit writing. So this is a cobalt chromium film, and what they do, they magnetize up and down areas, and you can use this colloidal method to illustrate the recording. So this is actual information written on cobalt chromium, and they're written at different speeds, and then you can they show how this information can be decoded using that. Okay, so this is just to illustrate you the application of that method. So although it was done quite some time ago, it is quite modern. The other application, the other method that can be used to visualize magnetic domains is something that you saw in my laboratory when you visited it. So it is called Magneto-Optical methods, and it's abbreviated to MOOC. It's Magneto-Optic Kerr effect. So let me write it down. Kerr effect. So Kerr effect, and side by side with Kerr effect there is this Faraday effect, is basically an optical way to measure magnetization. So if you would like to measure magnetization, what you can do, you take your sample and you shine light on it. Light, if it's a reflective sample, then light gets reflected, If it is transparent, then light gets transmitted. Oh no, this is not right. It would go almost the same way. Let's go. So light comes in, it reflects, transmits, dependent on the material. So if you have transparent material, some of it will reflect, most of it will transmit. In materials that we study, let's say if you'll take cobalt, iron, nickel, and other metals, metals are shiny and metallic, so there will be no transmission. But if there is transmission, then analyzing the light transmitted through the magnetic material would be called the Faraday effect. Faraday effect, and analyzing reflected light is our Kerr effect. So Kerr effect and Faraday effect. So what is done is that you shine the polarized light. It can be circularly polarized light or it can be linearly polarized light. You shine on magnetic surface. Then when the light is reflected, it has certain polarization direction, and it turns out that when light reflects off the magnetic material, the polarization rotates. So light polarization is a side note. So your light has two components. It might have E field, it might have, it has H field, and they oscillate. And typically in light that is just ambient light, typically light is not polarized. So this E field has totally random orientation, and it is random both in orientation and in time, so it changes all the time. However, if you have made the light so that your electric field is only in one direction, and it oscillates, so it's a wave of oscillating electric field, but electric field oscillates in one direction, that is called a linearly polarized light. Then if your electric field rotates as a function of time, that would be a circularly polarized light. So this polarization of light is used to make magneto-optic Kerr effect measurements. So if you shine light with the electric field pointing in a certain direction and you detect light, then it turns out that the angle theta, so the polarization rotates after reflection of the magnetic surface, and that rotation depends on the magnetization. If it's magnetized one way or another, you might have rotation, the light rotating into the different directions. So typically these angles, the rotation angles are very small. They're milliradians, but it's still possible to detect them. And when you visited my laboratory last time, I showed you the actual optical setup that does that. Now there are different ways. It turns out when you have reflection, if you apply field perpendicularly to the sample vertically, this is magnetic field H, then we are magnetizing film along the field. And it turns out that in this case, with the field applied vertically, we are sensitive to vertical magnetization. But not only to that, so typically this is called polar geometry, polar MOC. MOC stands for magneto-optic Kerr effect. So that allows to measure magnetization at this point where we shine light. And typically it's done at normal incidence, not like shown here in the picture. Now if we reflect light, same way, we reflect light off the surface. This is the magnetic surface. And if you apply field in plane, then this is called longitudinal. Now, if we apply field perpendicular to the plane of incidence, then H. Then this would be called a transverse geometry. Okay, transverse MOC. So the difference between these three geometries is that typically this one polar mode is typically done at normal incidence, so light comes in and goes back at normal incidence, and it is sensitive to magnetization, out of plane magnetization. These two are sensitive to magnetization along the field. And along the field direction, and actually not along the field direction, it is sensitive to magnetization along the plane of incidence. Okay, so what do we do to image domains? How we use that? First of all, of course, if you have material with one part of the sample pointing, magnetization pointing up, another one pointing down, we can shine light here, see one rotation, and shine light there, see the polarization rotation, and see that they're different. More than that, if you have a sample, we can mount it on a stage with a micrometer here and rotate the micrometer so that the stage can move left and right, and measure basically the rotation, and it would be one way and it would be the other way as a function of distance. But it's not, it's time consuming, although some systems are doing. So what we are doing here, we use a laser light and we scan the sample by moving the sample. So laser points in the shines on the fixed point, and we move the sample. So that technique is doable, but you have to move the sample in this direction, and also you have to move the sample in this direction, so into and out of the screen. Alternative would be to use a regular microscope. So what is done is you have the sample, and sample is placed in the magnetic field, and then you use microscope objective. It looks like this. There is optics inside, and you shine light, so there should be a light source. Now we don't deal with a laser, we deal with a light beam, so it's a broad light beam. We polarize the light, this is polarizer. We shine light, so light comes to the sample, focuses on the sample, and then reflects back. So reflected light going back, we put a semi-transparent mirror, which is called beam splitter, and that mirror would reflect the light reflected of the sample back. We would put it through the lens. Oh no, we would put it through another polarizer, which is called analyzer. So this is polarizer, this is another polarizer, which is called analyzer, and lens would focus the image into the camera. I think I showed you that as the system that I also have in my lab. So image is projected into the camera, and camera basically records not one point as we measured here with the laser, but rather it records the image of the area imaged by the microscope objective lens. This is just a lens, it's a complex lens. Okay, so let me show you a video if I can. So here is the video from YouTube, from Quest Integrated. They're selling their imaging systems. So it might look a bit strange, but here are the areas of high magnetic field, and these small curvy lines, dendritic type lines, are the magnetic domains. And this is an image taken through a microscope, and beauty of this technique is that it allows you to apply magnetic field and do simultaneous imaging. So currently I don't have access to my computer, but I'll show you my experiment in a separate video. But if we play this video, then you will see that that magnetic fields is getting changed, and as the magnetic field is changed, then these domains change their shape. You can see they're alive. So what they do in this experiment is they are changing the magnetization, and you can see that. Okay. So that is the film that they are measuring. This is a magnetic field. Okay, so let me turn off this video and let's carry on. Alright, so the magnetoptics is a very powerful technique, and it allows imaging magnetic domains. Magnetic domains can be in various shapes, and by analyzing these domains we can conclude something, you can make many conclusions about the magnetic material itself. Alright, so the domains. So we define domains as small regions in ferromagnetic materials within which all the magnetic dipoles are aligned parallel to each other. So now let's look at how they are formed domains. So to do so, let us recall something about demagnetizing fields. So let's look at the magnetostatic energy of magnetic moment. So let's take a piece of magnet and imagine that this magnet is magnetized. So there is north and south. So it's all magnetized in one direction. So if you look at the magnetic field lines, there will be huge magnetic field lines around it, right? Looking like ears. Oh well, that's not accurate enough, so they are not going to this point, but rather they start and go into this. Well, it doesn't matter, you know. I'm not good at drawing, but you know what I'm going to draw, what I'm drawing. So if this magnet has a single domain, then there is, and single domain means pointing this way, there is a huge demagnetizing field inside, pointing in the opposite direction. So demagnetizing field. So what it means is that we have a magnetic moment in presence of the magnetic field that points in the opposite direction. So let's look at the energy of magnetic moment in magnetic field. So to look at the energy, I think that I already mentioned that, but work done. So if you have magnetic moment and we apply magnetic field, then work done in general work can be calculated as F ds, right? Now, or we can explicitly, this is a dot product, so we can write it F sine theta ds, or that can be written as R F sine theta d theta. So instead of writing ds, we converted it to R F sine theta d theta. So now if you look at this, then you would see RF sine theta is it's a torque basically applied to the material with a negative sign. So we can write that work is equal to negative torque d theta. Now torque, if you recall, torque applied to magnetic field, it's M cross B, right? So that is MB sine theta. Let's prime it, d theta. And that is basically the work done to rotate the magnetic field, and we have to integrate from theta 1 to theta 2, different angles, depends on how we are it. So then energy of magnetic moment in magnetic field would be equal to work with this, I forgot, minus MB, and if you integrate this, that would be cosine theta, which is actually M dot B. Dot product. Okay, so it's quite thick. You can pause the video if you would like to. I remember you were asking about that. But if you look at that, if you look at alignment, so you would see that if we have magnetic field pointing in this direction and magnetic moment pointing in the same direction, the other possibility is magnetic field pointing in this direction and magnetic moment aligned in the opposite direction. Then that would be our low energy state, and that would be high energy state. So the difference between these two energies, and there would be a zero energy because it's a dot product. Zero is reached right when they're perpendicular. So delta U is 2mb. M is the magnetic dipole moment. B is the B field, so N can be related to magnetization M times volume of the material, and B is our mu naught H plus M. So this is the magnetization right here. Okay, so now what it turns out, what happens is that if you have a single domain, it would be unfavorable for the magnetization to be aligned along this demagnetizing field because it's a high energy state. So basically, single domain state is very high energy state. So in order to low down this, so what happens is that instead of having this material magnetized, oh, that's quite a curvy magnetization, magnetized along one direction, this system breaks into the domain. So basically, domains are formed to lower down the magnetostatic energy. So it breaks into two domains. One is magnetized this way, other one is magnetized that way. So in this case, we have north and south, south and north. But now if you look at this, the magnetic field is not huge outside. The magnetic field only goes from here to there. So it's much smaller area in space, and the rest is inside, and it is aligned. Now, similarly, this is not favorable state. So what can happen is that it can break into smaller domains. So it can break into domains pointing up, down, down. But still, for these domains, you would have magnetic field outside. So this is magnetic field lines H. Yeah. So these are the outside magnetic field, and it still is not energetically favorable. So instead of having this, what happens is that typically, it depends on the size and shape of that, but typically what happens is that it is energetically favorable to form a closure domain, so-called closure domain. So this area magnetized that way, this area stays magnetized that way, but there is another domain. So it's quite an ugly domain. Okay, and these areas, so let me use different color. This gets magnetized this way, this gets magnetized that way. So we have 1, 2, 3, 4 domains, and they form sort of a closed circle here in the material. And of course, it depends on the shape. As you remember, there is shape anisotropy involved here and crystalline anisotropy as well. But for materials like iron, it might be a cubic anisotropy. Iron is has BCC lattice, and easy directions are 1, 0, 0 or 0, 1, 0 for iron. For nickel, it's a different direction. So anyway, so that is how domains are formed. Now, if we look at the effects of these forming domains, then you can We can talk about magnetostriction. So it sounds like it's a different topic, but it's closely related. So now imagine that you have a material which has certain domains, and your magnetization is aligned like that. You can think of molecular magnetizations or domains, but if you remember, the material is typically aligned. There is a crystalline crystal structure, and there is crystalline anisotropy. For example, if you have a structure where you have different spacing between magnetic atoms, then atoms would interact strongly in this direction, and there will be weak interaction in that direction. And imagine that, for example, they align themselves this way. There is an interaction between these moments. So if I apply a field that way, I can force them to be aligned in this direction. But what would it result in is that the interaction between these and this and these and this, it defines the atomic space, it defines interaction and vice versa. So what can happen is that if we would apply a field in this direction, magnetic moments would align themselves along the magnetic field. But it depends on the material, but what can happen is that the length of this material would increase as well, because we would change interatomic spacing. This phenomenon is called magnetostriction. And magnetostriction basically is the length change caused by the alignment of magnetic moments. Magnetostriction can be used in both directions, so we can apply external magnetic field to change the length of the material, or we can compress the material to generate the magnetic field. And this is the magnetostriction. And magnetostriction is actually a very useful phenomenon. So there is a coefficient of magnetostriction. It's lambda. It's sometimes is the length change over the relaxed length, how much we change length. But at the same time, sometimes it's also related to the magnetic field that's applied. Where it is used, I'm not going deep into the details, but in general, there is lots of use. First of all, if you know what transformer is, transformer that converts AC, lowers down the voltage, or it can transform voltage to high voltage levels. If you listen to the transformer, they have a very specific humming noise. So that humming noise comes from the magnetostriction, because transformer has the coil 1, coil 2, and these coils are, there is a common core, transformer core. I draw it schematically, but this is a thick, okay, let me draw it thicker. It's made of transformer steel. So what happens is that you magnetize, you demagnetize. So you move magnetic moments within the core. And let's say if you're in the United States, that is done at 60 Hertz. And 60 Hertz implies that you're moving magnetic moments back and forth at 60 Hertz frequency. And that results in the shape change. So shape of this core changes at frequency of 60 Hertz. And radiates the sound, so it produces 60 Hertz sound, and it can be harmonics as well. So, but this is a harmful application. We don't want that. We lose energy that way. But there are specific industrial vibrators. So when you want to vibrate something at high frequency, so you build a what you can do is you build a core made out of the magnet, put a coil around it, and apply alternating voltage to the coil. Coil magnetizes and demagnetizes at certain frequency omega. And magnetization and demagnetization results in shape change. So this thing can get longer or shorter at this particular frequency. So that surface, and it's not only that surface, the whole thing vibrates. So you can make vibrations. Where that can be used? Well, you can vibrate things where you need it. But this is the principle that's used in ultrasonic cleaning devices. So you can produce sound at ultrasonic frequencies, and that would result in cavities in water, cavitation process, and that can be used to clean things. It is also used in underwater sonar systems and also in vibration and noise control systems, because you can use this to control vibrations and to produce something that counteracts to vibrations. So it's magnetostriction is used in many things and many applications. Okay, so now going back to domains. These are the domains, and we learned how they form. By the way, if you go back to the closure domain, that is the closure domain in iron. This way, that way, that way, that way. It turns out that actually the domains are, when you would like to form a domain, then there are certain ways how domains can be formed. And in the domain structure, the magnetostriction plays also a very important role. So the domains themselves, if we subject this magnetic domain to, let's say, magnetic field, internal magnetic field, it would want to be elongated along this axis. And naturally, because the area is magnetized that way, the natural domain would be bigger, and would be bigger, implying that following this magnetostriction effect, when it's all magnetized in this direction. But at the same time, if we will take this domain, it is magnetized that way, so that domain wants to be bigger in this direction. So, and therefore there would be a certain strain induced in the material. So at all these boundaries between domains, there would be a certain strain related to magnetostriction. Okay, so now let's look at the domains. So imagine that you have one domain and another domain. So boundary between two domains is called domain wall. So domain wall is a boundary between two areas of the magnetic ferromagnet magnetized in two different directions. So, and we will talk about domain walls now. This is the last topic of this lecture. So first of all, if you look at these domains, this one is a dipole. It produces magnetic field in this direction. So this magnetic field is favorable for this magnetization alignment. So dipolar fields. They basically help domains to form. On the other hand, this is a ferromagnetic material. And if you look at two magnetic moments, atomic magnetic moments here at the boundary, if you recall, there is an exchange energy. And in ferromagnets, exchange energy is not favorable of forming the domains, because these two want to be aligned ferromagnetically. We talk about ferromagnetism. So they want to be aligned ferromagnetically, but we are misaligned, and this is non-favorable alignment. So there are different types of domain walls, and we will talk about those in detail now. So first of all, it is energetically unfavorable to form a domain wall that is happening abruptly. So one up, one down, it is unfavorable. In general, what happens is that you have one magnetic moment here, other magnetic moment there, and there is a gradual change from these to that. So it might be tilting, and finally aligning. So this alignment, dipolar fields which play in favor of forming domains, dipolar fields are long range fields. So that means that the fields from this one interact with this magnetic moment. Exchange interaction is a short range interaction, so it favors alignment of near and neighboring spins, but it can be fine with alignment of two magnets in opposite direction if they are far enough. So each two of these magnetic moments are aligned almost parallel. So these two are pointing in the same direction, these two are roughly pointing in the same direction. Then that way we satisfy the minimum in exchange energy, or close to minimum. At the same time, so domains are not an abrupt boundary, but it has a certain domain walls. Domain walls do not have abrupt boundary, but there is a certain width across which this switch is happening. This switch is domain wall, and domain wall has certain thickness. We'll use delta to describe the thickness of the domain wall. There are different types of domain walls. There is different types of domain walls. Let's start with the simplest. So if you have If you have magnetization pointing this way, and you have domain wall, and you have magnetization pointing that way, that's domain wall. Alternatively, it is the same situation where you have domain wall and this too. You see the magnetization rotates 180 degrees, so that's 180-degree domain wall. You also can have a 90-degree domain wall. So magnetization points here, domain wall, magnetization points there. Actually, it can be 90. So that's a 90-degree domain wall. And if I scroll up right here to closure domain, you can see that this is at 90 degree to that. This is a 90-degree domain wall. This is 180-degree domain wall. There are also 360-degree domain walls where you have magnetization pointing this way. You have area, and again 360. So 360-degree domain walls. So also, how do you go from one orientation to another? So you can go, I can draw you this in this form. So if this is a material, and imagine you have one area magnetized this way, here's a domain wall, and this area is magnetized that way. This is pointing there, this is pointing here. So in the middle, you can have in-plane rotation. So basically, you rotate this in plane, and in the middle of that, you would have magnetic moment pointing in this direction. So this is called nil domain wall, when the magnetization rotates in plane of the magnetization alignment. So if you have an axis, if I would draw this transition, I would see this is pointing up, tilting, and pointing down. So this is nil domain wall. So if you take a plane of the magnetization, then magnetization rotates in plane. The other type would be called block domain way. Let me draw it again. So here's the magnetization this way, and this is magnetization the other way, pointing that way, pointing this way, point this way. Okay, so material is magnetized, and this is a domain wall in between. So if rotation of the magnetization happens out of plane, which means that here our magnet would rotate about this axis. If I scroll down here, this magnetization rotates about vertical axis. So we have vertical axis and it rotates in plane of the magnetization. Here it rotates out of plane. So it would start to tilt, and in the middle it would be pointing, let's say, up, and it would be pointing upward. It's hard to illustrate, but if we look along this axis, then magnetization is pointing this way, then it rotates. In the middle, let me draw it with a different color here. It points up. It rotates there, it points this way, and it then rotates, and at the end it points down. This way. So rotation happens along this axis. And in this case, in the middle, the magnetization, so it starts to tilt, it points up, and then it tilts that way, and then it points down. So it's hard to visualize rotation since I have poor drawing skills, but that's it. This is called a block domain wall. These are just different types. Now it all depends on the interaction between the materials and on the strength of dipolar fields, on the exchange interaction, and if there are other interactions involved. Okay, we introduced domain wall. Let's look at the exchange energy. So if you remember, exchange energy is -2 exchange integral s square cosine phi ij. So if you have one spin as I, other spin as j, and there is a certain angle between them, that would be angle phi. Okay, so this implies, this factor suggests that it's unfavorable to change the magnetic moments abruptly from up to down. So this term cosine phi j suggests that it would favor the gradual change. So therefore we would deal with the very, very small angles, and we can write our exchange energy as -2a, cosine d phi dx. So we have this gradual change to opposite direction. This is our x direction, and that would be the d phi, the small change between neighboring spins. A, now we wrote down A is n j s square over A. It is called exchange stiffness constant. Now in exchange stiffness constant, we have n. N is number of atoms per unit cell. And we have A. A is a lattice constant. So if you have the rectangular lattice constant would be this. But you should know that from solid state course. Now A, you can see this is energy, right? It's the same as there. So units for A are joule per meter, or in CGS units are per centimeter. They're not equal. So A is a macroscopic equivalent of exchange energy. So you have exchange energy that describes the interaction of neighboring spins. A basically describes the energy, but at the macroscopic scale. Okay, now let's look at this thing. If you look at cosine function, let's expand it. Cosine phi, 1 minus phi squared over 2 plus phi 4 over 24 minus etc. So it's an expansion. So we will expand cosine function, but we would drop all terms of higher order and use only these two terms. So with that, the exchange energy can be written as you can see it from here. So we basically expand this cosine function in exchange energy. It's minus 2a plus a d phi dx squared. Okay, so this is independent of the angle. There is no phi involved in this term. This is angle dependent term. So we don't care about this one, we would care about that one. So exchange energy, E exchange, would be equal to a d phi dx squared. Okay, so exchange energy is one energy that defines the alignment, but there is a trade-off between two different ones. If you remember, well, dipolarization is a long term, let's not talk about that, but why would our material be magnetized in one direction or another? So, for example, iron, it wants to be magnetized along a certain direction, and if you remember, that is anisotropy. So the second energy taking an important role is anisotropy. Anisotropy. So anisotropy is a certain function of A. Anisotropy is a certain function of angle as well. And as you remember, that is lecture number 1, I think, online lecture number 1. Anisotropy, let's take, if you take uniaxial anisotropy, this function would be anisotropy constant sine square phi. That's for uniaxial anisotropy. For biaxial anisotropy, that can be, or cubic anisotropy, let's say cubic anisotropy. That's sine square phi cosine square phi. That's cubic. So that energy is something that we already discussed. And the system has lowest energy when magnetic moments are aligned along the easy axis. And system has highest energy when it is misaligned. So if you look at our domain structure, where is it? Let me choose this. Then exchange interaction would want to align these two parallel to each other. At the same time, within this area, if you forget about dipolar, I have to exchange, I have to add another term here, is anisotropy. And anisotropy actually favors abrupt change, because it is favorable for magnetic moment to be aligned vertically if this is easy. Vertical is easy axis. If vertical is easy axis, then this one wants to be aligned vertically. This is least favorable alignment to be in. So therefore, for all these, the anisotropy energy favors them to be aligned vertically, either up or down. Now let's scroll to where we are. And this is the expression. Okay, so now from this we can look at the energy stored in the domain wall. So domain wall, and we can talk about domain walls, but typically let's talk about the surface energy, because domain wall is a surface. It's a surface between two areas with the same domain. So for the surface energy, I'll use sigma, and it's energy per surface, which would be comprised of exchange domain energy and anisotropy energy. And to calculate that, we basically have to integrate over the material. So we integrate our exchange d phi dx square, this is d phi dx square, plus g phi And we would integrate a dx across the domain wall, but we can go from minus infinity to plus infinity. So if you have domain wall going from one spin to another one, then we basically integrate this energy in this direction. And we integrate it because here is angular dependence of exchange interaction here and angular dependence of anisotropy. So now energy can be related to torques. So torque, I'm scrolling down, but you can pause my video at any time and record it to your notes. I actually encourage making notes. So exchange, torque related to exchange is d e exchange d phi. That would be the torque. That is a d d phi dx square d phi. Okay, we take derivative of this. That's 2a d phi dx d d phi dx d phi. That is 2a d phi dx d2 phi dx square. Oops, I missed one term. What I missed is dx d phi. We took this is derivative of a square function, 2a times derivative of the function itself. Then when we take derivative of this, that is what it is. So we take d phi dx square and dx d phi. Okay, so what it leaves us, you can see this go away. That leaves us with 2a d2 phi dx square. Okay, that is our torque. That is torque due to the exchange energy. Now imagine that if angle between neighboring spins, so if this d phi is constant as a function of x, so basically each two neighboring spins are twisting on the same angle, then what it would mean, actually not d phi, that would mean that d phi dx is constant. If d phi dx is constant, then our torque due to exchange is equal to 0. So basically, if you turn spin with a constant angle, then there is no torque on spins, and they would be turning. Okay, the second part is anisotropy energy. Anisotropy. So anisotropy, again, torque related to anisotropy is dE anisotropy d phi. And basically we have to take derivative of that g function, which depends on the type of anisotropy we use. Now at equilibrium, if you have equilibrium, these two torques apply to the system. Torque due to the exchange and torque due to the anisotropy. They should be equal, that opposite in directions. So that's in equilibrium. Okay, so what it would mean is we can substitute those two. So 1 second. Okay, so this condition for equilibrium means that the exchange energy should balance the anisotropy energy, and torque generated by exchange interaction should balance torque generated by exchange. So we can put the torques, here is torque for anisotropy, and here is torque for exchange, so we put them together, and we can write that dg as a function of phi d phi plus 2a d square phi dx squared should be equal to 0 within the wall. So within the wall. Okay, so now in order to find our goal is to find basically the angular distribution of magnetic moments, and that would depend on the anisotropy. But what I would do, I will do it pretty quickly. So there, and you can pause the video and think about that. There are two terms. Term number 1 is this one, and this is term number 2. So I'll address those separately. But first, what we will do to both of them is we will multiply this equation by d phi dx, and then we will integrate it over there across the wall. So term number 1, that would be integral d phi dx. We multiplied it by that dg d phi dx, integrate across the domain wall boundary. That would be integral of dg. That is our g as a function of phi. Pretty straightforward and quickly. Now the second term is we have to integrate d phi dx, and there would be 2a d2 phi dx squared dx. 2a goes outside, d phi dx. Now we put this under, we take this to represent it the following way. So it's 1/2 d phi dx dx. So we are going backwards, same way as we were going here. We are going backward. We went from here to there. Okay. Then what we do with this is that there is not that much, so you can continue doing that, but basically that would be a coming from this 1/2 goes and d phi dx dx. So what would be left is d phi dx squared. Okay, so if you combine these two and write our expression for torques using what we found, we will see that a d phi dx squared should be equal to g as a function of phi. Okay, so there are many things that we can do. First of all, even if you don't know this, we can solve this one way or another. So we can write that d phi dx is equal to g as a function of phi over a, take square root of that, from which we can find dx is square root of a d phi divided by square root of g. And from this we can find that x is equal square root of a, and we'll have to integrate d phi divided by square root of g as a function of phi. So this, I think, is the main result. Now, what did you find here? So you have one magnetic moment pointing in one direction, other magnetic moment pointing in the other direction. This is x-axis, and phi is the basically angular distribution. So how angle between, not between, but basically how angle orientation of the magnetic moment would depend on x. So how it would rotate, how this rotation would be happening. So this is the phi angle here. And we are looking for phi as a function of x, or x as a function of phi. That would be in here. Now, of course, we can do that if we know what type of anisotropy we have. So let's work out the example. So first, 180-degree wall, uniaxial anisotropy. So for uniaxial anisotropy, g of phi is uniaxial anisotropy constant, sine square phi. So you can substitute it in this and integrate it. So what you will get is the following. You'll get x equal square root of a over ku natural logarithm of tangent phi over 2. So that is a result for uniaxial anisotropy, and you can get that by integrating that. So now I will use this feature to get the coordinate system. We would be, this is phi, this is x. You can invert this, but in general, if we plot this function, here is another line and another line. So this is 0 degrees in phi, this is 180 degrees in phi, and this is 90 degrees. So what happens is that it would approach this. You see, you have tangent here, but when we'll invert, it would be horizontal. So it would go from here and there. So there will be a gradual change. So if you look at spins here, it would be 0, pointing up. Here it would be 180 degrees, pointing down. Now in the middle, it would be at 90 degrees. So it would be pointing this way, at 90 degrees. And in between, there is a gradual change. So you can see it changes from from 0 to 180 degrees. Now formally, if you look at this function, you will see that this is formally an infinite wall because it approaches 0. There is no certain place where it would be absolute 0 or absolute 180 degrees. It approaches this value. So in order to measure the domain wall thickness, what we do is the following. We look at the slope in the middle and we draw a line with this slope. And it's not the best color. Let me duplicate it. So this line would give us a certain area. And that area is basically what would be considered a domain wall width, delta. Now, we would say that domain wall thickness here, we would say we would take the slope in the middle where the spin is at 90 degrees. We would take the slope and extrapolate it. This is what conventionally is taken as a thickness. And if you would calculate that for this case, then thickness would be pi over square root of a over ku. And domain wall energy stored in the domain wall would be equal. You can substitute everything into the energy. That would be equal to 4 square root of a ku. So now these energies, they can be calculated. So if you will take iron, I could do an example of iron, but before we do so, iron is actually a BCC lattice. So for iron, it is not uniaxial anisotropy. For iron, it is cubic. So what we have to do, we have to take cubic anisotropy, substitute it into the, take the integral for cubic anisotropy type, and calculate. So for iron, the resulting solution of that would be a over k cubic logarithm of tangent phi, and the domain wall energy would be for a k cubic. Now, the way how you calculate it for cubic anisotropy, there are two easy axes. So there is easy axis pointing this way, easy axis pointing that way. And therefore, instead of having 180 degree domain wall, you separate that into a 90-degree domain wall, and then plus another 90-degree domain wall. So energy would be combined of 90-degree plus another 90-degree domain wall. And you saw that closure domain for iron. But in general, if you would calculate for iron, J is 4 times 10 to the negative 14 erg. Again, using CGS units. I told you in the very beginning we'll be using those. Exchange stiffness constant is NJS square over A. And if you calculate that for iron, we have 2 atoms per unit cell, 4 times 10 to negative 14. Spin is 1/2 square, divided by lattice constant, 97 times 10 to the negative 8. So that is approximately 7 times 10 to the negative 7 erg centimeter. That can be converted into joules. That's approximately called 7 to 10 to the negative 12 joule per meter. Now, for cubic anisotropy, we can calculate energy, domain wall energy stored in that, AKC, and that is approximately 2 times 10 to the negative 3 joule per meter cube and meter square. It's a surface energy, and we can calculate the domain wall thickness. That is our pi A over Kc. Did I write it down here? Let me see. Oh no, yes. So we use this for cubic anisotropy, and it's the same for uniaxial. That would be approximately 4 times 10 to the negative 6 centimeters, which is 40 nanometers. So 40 nanometers is the domain wall thickness in iron. So 40 nanometers, if you think of iron, the lattice spacing is, I use it here, this is the lattice constant, this value. So it's approximately 3 atoms per nanometer. Well, something is not right, it's not 8th, it's 11th. Yeah, it's 2.8 angstrom. Let me erase it. I know how to erase things. Yeah, so angstroms is negative 10 of meters. Oh, negative 10 of meters, but we are in CGS, so it's negative 8. That's correct. That's correct. Okay, so we have on average 3 atoms per nanometer. That means that if you multiply it by 3, that would be approximately 120 atoms thick domain wall. Okay, so that is what I would like to tell about domains. And if I scroll back, then there are different types of domain walls, and these different types of domain walls are, again, it's a trade-off different energies. There is exchange energy that wants magnetic moments to be parallel. There is anisotropy energy that wants domain magnetic moments to be aligned along certain directions. And there is also dipolar forces that the dipolar forces that favor the opposite alignment of antiferromagnetic alignment of magnetic moments. So all these combined together form the domain walls and define the shape of domains, and the shape of domains is also defined by anisotropy, because the crystal structure defines what are the easy axes, what are the hard axes, and how this is distributed throughout the crystal. All right, this is the end of the lecture about ferromagnetic domains.